Hello guys, welcome to my YouTube channel. Today we are going to see how to run a Rust application in embedded system. And for that you need to have certain tools installed in your PC. And these are the tools that are required to run the Rust system, Rust in your embedded systems. So take a screenshot of this and make sure to download all the tools that are required. And diving into the project creation. I'm currently using a Linux-based PC, so I'll be doing all the folder manipulation and everything using terminal. And I just opened WAP terminal, which is AI-based terminal, and in this I'm going to navigate to CD developer slash embedded. In this folder, I'm going to create a Rust project using the template from cargo generate. So for that, I'm going to enter the command as shown in this as shown on the screen. Cargo generate git and the templates, and this is a repository given from Rust. This is a basic template from the Rust official website. In this, it is going to ask you for the project name. I'm going to give it Rust tutorial, and after that you'll get successfully created, and you can find the folder with Rust tutorial name. I can enter into Rust tutorial, and in this I'm going to open it in IDE. I'm currently using cursor IDE, so I'm opening it in cursor. Cursor is a AI based uh, IDE, which is quite helpful when you're working with uh, projects, and it has Rust extension supports also. So it's quite helpful. So please make sure that you are using any kind of idea of your wish. And in here you can find this is a template that we have generated using cargo generate. In this you can find dot cargo. In dot cargo we have config.toml. So config.toml will consist of the targets that we are going to set for the board, and the commands uh, that are required to run using cargo. So here you can find at the last for build we have target set with Cortex M3's target. Currently I'm using a Cortex M4 based board, so I'll be commenting this and uncommenting the Cortex M4's configuration. And I'm going to run examples. In this example I'm going to run hello.rs. So the hello.rs, we have hello world print on the console. So um, in today's video I am going to run this and run this on the STM32 board. uh, and we in this template we have source. In this source we have the main function. If you give cargo build, the main function will get executed. So currently I'm not doing the main function executor. I'm going to build the hello world project, that is hello.rs for examples. So to build that, first we need to set target for STM32, so that the configuration is set with Cortex M4's configuration. For that, I'm going to enter the rust up target add command with the target's name. For us, it will be Cortex M4, so I'm using this and add it here. Save this config.tyml file, and then after saving, you need to enter cargo build, and in this I'm going to build the example code, so that I'm giving double dash example and hello. As I already set the configuration with Cortex M4's configuration, uh, you don't need to give the target when you're entering cargo build. And once you're done, you can find a target folder has been created on the left side. Inside we have the configuration name that we are using, and inside that we have debug, and inside that we have examples, and inside that we have hello. So this is our ELF file that has been generated after running cargo build. So this is the file that yeah, we are going to load into the board and run. And to check the properties of this file, we can use cargo read obj file, read obj command, and I'm copying this and I'm pasting it here. Here cargo read obj, and after that I'm giving the name of the target, name of the ELF that I have generated now, and double dash headers will give out the print out the header details of this ELF. So as you can see, we have it has given us the class that it has been created. Yeah, it is an ELF32 file. And we have program headers address, and um, we have entry point address, and what type of mission it is going to be, and executable, is it an executable or not, or is it a library. So this kind of information we will be getting from read obj command. And we have uh, another command, cargo size, which will print out the size and addresses of the ELF that we have generated now. So make sure to use the same command as in, and only the binary file name you have to change when you are running it for your specific ELF. And we have here the sections of the memory segmentations, and we have .bss starting at and we have .data and text at 400. So by this we can understand what are the data segmentation that is present inside this ELF. And this is helpful when we are running it on the real board. As of now I'm showing it on QEMU. So for QEMU you don't need any memory configuration perfectly aligned, so because it is a simulator, so you don't need to worry about it. When you are running it on a board, make sure to use the memory configuration correctly. And to check the disassembly code, we need to use this command. Yeah. So here we have the disassembled code. As you can see, uh, we have main here at 400, and it's quite difficult to understand this ASM code, but use this command properly so that you can have a ASM code, and you can analyze it when you want to see the insights of the ASM. And after this I'm going to run this ELF on an QEMU simulator. For that I'm going to use QEMU command. So this is the command I'm going to use. So in this I'm telling the command that it's going to use Cortex M4 and mission LM3S. This is STM32 mission configuration name, and we have no graphic, and semi hosting enabled is on, and we have target as native, and we have kernel set, and we have kernel. You need to connect this GDB TCP before terminal kernel so that it won't get any errors. um, GDB space TCP 3333. and the kernel what the um, ELF that we are loading has to be given in here after kernel. And when you run this debug examples hello, yeah, this is the correct path. And after running it in QEMU system, you can find the hello world has been print. That means it has run and successfully came out. uh, and this is a simple run configuration. If you want to debug this in the simulator, then you need to use dash s before GDB, so that it will stop at startup, and it will wait for our command to come, and then it will execute the code. Slash s, it is waiting for a command. And in another terminal, I'm going to connect it using GDB. So this is left side we have QEMU, on the right side we have GDB. And for GDB, we are going to use a command called as GDB multi-arc command for, and then we are going to set the executable with our hello. And I pasted this command, and by clicking enter, it is reading the symbol from hello, and it has loaded. And for it to load, we need to enter load command. Okay, it I think it's actually need to load. You can directly connect the target with the target remote 3333, and you can see it has been connected, and it is reading from the text at 400, which you have seen previously when we have run uh, cargo size. That is the starting of text, that is code's memory. And here we only have a warning, so no need to worry. After after target setting, we need to set breakpoint at main. So by giving break main, it is set a breakpoint 1 at 400, at which will be the starting line of the main. We can see the code that has loaded by entering list main. So this will print out the code that is present inside the ELF. And after this, you can con- enter continue, which will hit the breakpoint at main. And after that, I'm going to queue step, so which will go into the inside the main. As you can see in the hello.rs, we have entered here at this point. So after this point, if you want to go to the next, you need to give next, and it will print. So as you can see, I'm giving next. On the left side, you can see hello world has been print. And by giving continue, it will come out, and the process is completed. So came out of the command, and you can see with the successfully came out by entering echo uh, dollar symbol and question mark. It will print out the last written value. So it is 0, so that means it has successfully came out. And if you want to run this code inside the STM32 board, you need to make sure some configurations are set uh, before running. So one of which is memory.x. So in the main in the root directory of the project, you can find memory.x. In this, you can see there is a memory segment, and there are a lot of comments below. You can ignore those as of now, and um, you can you need to change the values of the flash address and the RAM address from the data sheet, the for which the board you are for which board you are using. The board I'm currently using is STM32. I'll show it on the screen. Please have a look at it. And you can buy this from the link given below. Mm. Or else you can directly go into STM32's uh, official page and download, get it uh, get it there. Or else you can find it in Amazon store. So connect the board now, and to check the connection is valid or not, we can I'm going to open a new terminal. In this new terminal, I'm going to run OpenOCD. So this will shows the connection that has been established. If you find the target has 6 breakpoints and 4 watch points, then your board is successfully connected, and you can communicate it using OpenOCD. OpenOCD is a on-chip debugger which is present inside the board. So you should have this inside your board so that only you can connect it with OpenOCD. And it has also given us with the type of processor it is using. So even though it has linked with STM32 F3X CPU, but it is showing M4 chip that is present inside. And we need to make some changes before running, as this template is having F3 configuration, and we need to change it to F4 configuration and save this file. And I'm going to close this. If I'm removing the connection now with the board and I'm running the OpenOCD, so that you can have what will come if there is no board connected. So this will be the error that will show when when the board is not connected, and when it's connected, you will get this kind of message. That means it has connected successfully. And to load this, so let's stop this OpenOCD for now. And before running the code inside the STM32, first we need to make sure the memory alignment is correctly assigned, and with our board's configuration. So different boards will have different memory configuration. So we need to make sure that memory configuration is set according to the board that we are using. So currently I'm using STM32F407. So I have a datasheet downloaded with me, and I am opening the datasheet. In this, you can search for memory map. Usually, in every STM32 board will have the same kind of uh, PDF. So you can search for memory map, and I have it right here. So yeah. So as you can see in this table, uh, we have flash assigned at 000, and we have SRAM starting at 2000000. Yeah. So this is starting address of SRAM. That means RAM's address, and I'm going to edit this address in the memory. So it is same here. You can remove the space between. And here we have 512 megabytes of data reserved for SRAM. So you can use all of that, or you can use part of it. It's up to you. And we have flash memory, that is so from here it has boot memory, and from here it has flash memory. So flash memory is starting at 800 um 0000. That so I'm going to copy this and enter the flash memory here. So I'm going to change it here, 8. So this will be our flash memory, and I'm assigning 256K for the flash memory. Usually we can give below 512 as 512 megabytes is present, and 512 megabytes is a top limit, and beyond that if you give, it will going to crash. So make sure to give the memory configuration properly. make sure to release this line. I've already forgotten about this, and you need to build it again. So because of that, I got an error. Build the hello program using cargo build. Hello example hello. Once you're done with the changes in hello.rs, you need to build it, and after that we need to open GDB connect OpenOCD connection. For that I'm using OpenOCD, and once the connection is done, on the right side you can see the OpenOCD is open, and on the left side I'm entering GDB command uh, by loading hello, and I've loaded. I need to set the target remote. 3333. After this I need to load the code. Once the load is done, on the right side you can see some changes has been done, and the address at which the code is present, and the both addresses are same on left side and the right side. And after this I'm going to enable semi-host. Semi-hosting will semi-host will let us use the console from for STM32 to print. Uh, so semi-hosting is enabled. After this I'm going to put a breakpoint at main. Break and breakpoint is set at main, and I'm going to enter continue. It has hit breakpoint 1, and after that I'm stepping in by using step, and it has entered into print ln function, and after here I'm going to give next. As you can see, by giving next, it has um, on the right side you can see hello world has been print. So this is how you can run a code on STM32. Now on the right side you can see this is the output from the board, not from our PC or anywhere else. It is came from the board that you have seen previously in the video, and so that's how you want to run Rust in embedded C. And on the left side, by giving continue, it is it now it's at a loop. As you can see in hello.rs, we have a loop, and it will enter into the loop, and it will uh, stay there until the interrupt is come. So so this is how we are going to run a Rust application in embedded C. You can modify the main.rs and play around with the code, and you can use the examples in the above example folders, and run one by one on your QEMU or on your STM32 board or any other board you want to run, and make sure to uh, have memory configured correctly, and config.toml target set correctly. Here you can use these commands by uncommenting them and saving this file, so that you can use the shortcuts to run the command. Here I will show you a small example. By saving this, we can run cargo run command, and this will use this command to run and we have OpenOCD.GDB. In that everything is configured, so it is going directly to the connection. And this is how you can use this .uml file to configure the commands and explore it. If you have any doubts, please let me know down in the comments, and I will help you solve those. And don't forget to like, share, and subscribe if you like the video. Thank you for watching the video. Until the next time.